Hold your hand up and look at the space just past your fingertips. It looks like nothing. No dust, no light, and if you went high enough, not even air. For most of history we thought that was the whole story, that empty space was simply the absence of things. It turns out empty space is filled with energy that never holds still, a restless background that hums along even when every last particle has been taken away. By some honest measures, it may be the most energetic stuff in the whole universe. Over the next couple of hours, I want to build that idea up slowly, one careful step at a time, and answer a single plain question. What is really there, inside the nothing? If a slow climb like that sounds good to you, take a moment to subscribe. We will start where everyone starts, with the simple feeling that empty means empty. Pour a glass of water and drink half of it. Look at the top half of the glass now, the part with nothing in it. You would say that part is empty, and in ordinary life you would be right. We learn the feeling of empty early. A box with nothing in it. A room cleared of furniture. The space between your hand and the wall. In each case, empty means the same simple thing, that the stuff has been taken out and what remains is plain absence. A stage with no actors, a container waiting to be filled. This feeling runs deep, and it runs honest. When you wave your hand through the air in a room, you do feel a slight push, because air is a real substance made of molecules. Take the air away and the push goes too. Climb high enough, past the last thin wisp of atmosphere, and you reach a place where almost nothing pushes back at all. That is the picture most of us carry of outer space. A vast, cold, silent emptiness. A nothing so complete that sound cannot cross it, because there is no air to carry the sound. For most of human history, the smartest people alive believed this was the end of the matter. Empty was empty, and there was nothing more to say. I want to spend the next couple of hours showing you that this picture, as natural as it feels, is wrong. Not a little wrong around the edges, but wrong at its heart. The space just past your fingertips, the space between the stars, the space inside the atoms that make up your body is not absence. It is a thing. It has structure. It holds energy. It trembles, very slightly, all the time, and it cannot be made to stop. And by some careful and serious measures, this restless background is the most energetic stuff in the entire universe. Far more than all the stars and planets and people combined. That is a strange claim, and I do not want you to simply take it from me. The whole point of what follows is to build it up slowly, one careful step at a time, so that by the end you can see for yourself why physicists believe it. We will start with the oldest and simplest idea of nothing, and we will watch it crack, again and again, each time someone looked a little closer. Every chapter will rest on the one before it, so you always carry what the next idea needs. Here is the plain question I want to answer. What is really there, inside the nothing? Not the nothing of an empty box, which is just air. Not the nothing of a cleared room. The deepest nothing we can make, the true vacuum, the space left behind when every single particle that can be removed has been pulled away. When you scoop out all the matter, all the light, all the air, and you are left with a region of pure space, what is sitting in there? For thousands of years, the answer was a single word: nothing. By the end of this video, you will understand why the real answer is far richer and far stranger than that. We will meet the people who chipped away at the old picture. A man who tipped a tube of mercury and made the first patch of real emptiness on Earth. Horses that could not pull two metal cups apart. A famous experiment that went looking for an invisible ocean and found bare floor. And the quiet line of thinkers who, piece by piece, realized that emptiness has a temperature, a tension, and a hum. So hold that simple feeling in your mind, the feeling that empty means empty. Honor it, because it served us a long time. Then come with me as we set it gently down. We start where everyone starts, with the very first people who dared to ask whether true emptiness could exist at all. Long before anyone could pump the air from a jar, The question of empty space was an argument among Greek philosophers, and it split them into two camps that could not agree. On one side stood the atomists, Leucippus, and his student Democritus, who lived more than 2,000 years ago. They had a bold and beautiful idea. Everything you see, they said, is made of tiny, hard, uncuttable pieces, and they called those pieces atomos, meaning that which cannot be cut. The whole world was just atoms, moving and joining and breaking apart. But atoms need somewhere to move. If the universe were packed solid with matter, with no gaps anywhere, then nothing could ever shift, because there would be no room to shift into. So Democritus and Leucippus insisted on a second thing alongside the atoms. They called it the void. The void was genuine empty space, real nothing, and it was just as necessary as the atoms themselves. Without it, motion was impossible. To them, the universe was atoms and void, particles and the emptiness they travelled through, and that was all there was. Against this stood Aristotle, perhaps the most influential thinker in the ancient world, and he found the whole notion of the void unacceptable. Aristotle argued that true empty space could not exist anywhere in nature. His reasoning was careful. He believed that the speed at which a thing moves depends on the thickness of the stuff it moves through. Push your hand through water and it moves slowly. Push it through air and it moves faster, because air is thinner. Follow that logic to its end, Aristotle said, and you reach a problem. In a perfect void, with nothing at all to slow a thing down, motion would have to be infinitely fast. A stone would cross the gap in no time at all. That seemed absurd to him, and so he concluded that the void simply cannot be. From this came a phrase that echoed for 2,000 years. Nature abhors a vacuum. The Latin form, horror vacui, the horror of the void, became a kind of law. The idea was that nature itself refuses to allow a truly empty region, and will rush to fill any gap before one can form. Suck on a straw and water climbs up to meet your mouth. Pull a piston back in a tight cylinder and you feel resistance, as though the space behind it is fighting to stay full. People took these everyday experiences as proof that nature would not tolerate emptiness, that it would always close the gap. Aristotle's view won, and it held for an astonishingly long time. Through the Roman world, through the Middle Ages into the Renaissance, scholars largely agreed that a real vacuum was impossible. The Church wove the idea into its picture of the cosmos. The void became not just a mistake, but almost a forbidden thing, a place reason said could not exist. There is something worth noticing in this old fight, because both sides were partly right, and we are still living with the tension between them. The atomists were right that the world is made of tiny pieces moving through space, a picture astonishingly close to the one we hold today. Aristotle was wrong that the void cannot exist, but he was on to something deeper than he knew when he insisted that empty space could never be a simple, harmless nothing. He felt, without the tools to show it, that emptiness was a problem, that it could not be left alone as pure absence. For now, hold on to the shape of the disagreement. One camp said the void is real and necessary. The other said it is impossible and forbidden. For almost 2,000 years, the question stayed a matter of argument, with no way to settle it, because no one could actually make a vacuum and look at it. That changed in a single afternoon in Italy, when a former student of Galileo filled a glass tube with mercury, turned it over, and watched a small patch of genuine emptiness appear at the top. The man who finally made emptiness was Evangelista Torricelli, an Italian physicist who had served as secretary to Galileo in the last months of the old master's life. Galileo had wondered about a practical puzzle that troubled the well-diggers of Florence. A suction pump could lift water only so high, around 10 meters, and no higher, no matter how hard you pumped. Below that limit, the water rose obediently. Above it, the water simply refused to climb. Aristotle's followers had no good answer. If nature truly abhorred a vacuum, the water should follow the piston up forever, to any height at all. Torricelli, working around 1643, had a different idea, and it was a radical one. Maybe nature did not abhor a vacuum after all. Maybe the water was being pushed up the pipe from below by the weight of the air pressing down on the open pool at the bottom. The atmosphere, the whole ocean of air above us, has weight, and it presses on every surface. That pressure could only push water so high before it ran out of strength. 10 meters of water was simply as much as the air could hold up. To test this, Torricelli reached for a heavier liquid. Mercury is about 14 times denser than water, so if his idea was right, the air should only be able to support a column about 14 times shorter, less than a meter. He took a glass tube sealed at one end and filled it completely with mercury. Then he covered the open end with his thumb, turned the tube upside down and stood it in a dish of mercury. When he took his thumb away, the mercury in the tube dropped a little, then stopped. It settled at a height of about 76 centimeters above the dish, and there it stayed, held up by the weight of the air outside. That was striking on its own, but the truly important part was at the top of the tube. The mercury had fallen away from the sealed top, leaving a gap, and that gap had nothing in it. No air had gotten in because the tube was sealed and the mercury had filled it completely before it fell. No mercury was there, because the mercury had dropped away. What remained was a space that held no matter at all. Torricelli had made a vacuum, the first deliberate, lasting patch of genuine emptiness anyone had ever created. We still call that space at the top of a barometer the Torricellian vacuum. This was a quiet revolution. For 2,000 years the void had been impossible, forbidden, a thing nature would not allow. Now a man in Italy had one sitting in a glass tube on his table, and could make another whenever he liked. Aristotle's horror of the void began to look less like a law of nature and more like a habit of thought. Torricelli had built something else too, without quite naming it. The height of the mercury column was set by the weight of the air, and the weight of the air changed slightly from day to day with the weather. He had made the first barometer, an instrument that reads the pressure of the atmosphere. He noticed the mercury rising and falling on its own, and connected it correctly to changes in the air itself. He summed up the deeper picture in a line that has lasted. "We live," he wrote, "at the bottom of an ocean of air." That single image rearranged how people saw their world. The sky was not a weightless nothing pressing gently overhead. It was a vast, heavy sea, and we were creatures at its floor, holding up a column of mercury with every breath. But Torricelli's vacuum was small, a thumb's width of space at the top of a tube. The next question was obvious and irresistible. If you could empty a little space of its air, could you empty a large one? Could you build a machine to pull the air out of a whole vessel, and what would happen if you did? That challenge passed north, to a mayor in Germany with a flair for the dramatic. The man who took emptiness from a tube to a spectacle was Otto von Guericke, the mayor of the German city of Magdeburg and an inventor of real gifts. Around the 1650s he built something the world had never seen, an air pump. It worked a little like a water pump run in reverse, with a piston and valves that let him draw the air out of a sealed container, one stroke at a time, until very little was left inside. For the first time, a person could make a large vacuum on purpose and hold it. Guericke had a showman's instinct, and he understood that a new idea lands hardest when people can see it with their own eyes. So he staged a demonstration that people still talk about. He had 2 large copper hemispheres made, each about 1/2 meter across, with rims that fit together cleanly. He greased the rims, pressed the 2 halves together to form a hollow sphere, and then used his pump to suck the air out from inside. Nothing held the halves together but the empty space within and the air pressing in from without. Then he brought in the horses. Teams of horses were harnessed to each hemisphere and driven to pull in opposite directions, straining to tear the 2 copper cups apart. They could not do it. In the most famous version of the demonstration, given before noblemen and in one account the emperor himself, around 30 horses, 15 to a side, heaved against the sphere and failed. The empty space inside held the halves together with a grip stronger than a team of horses could break. When Guericke finally opened a valve and let the air rush back in, the hemispheres fell apart in his hands with the gentlest touch. What the horses were fighting was not the vacuum reaching out to hold the halves. It was the weight of the atmosphere pushing in. With air inside the sphere, the pressure was balanced, inside pushing out as hard as outside pushed in. Empty the inside and that balance is gone. The full force of the surrounding air presses on the whole outer surface of the sphere with nothing to push back from within. Across 2 hemispheres 1/2 metre wide, that adds up to a load far beyond what the horses could overcome. Guericke had made the pressure of the air visible, turning Torricelli's quiet ocean into a public drama. Word of the air pump spread, and in England it reached a wealthy and brilliant experimenter named Robert Boyle. Boyle, helped by his assistant Robert Hooke, built a better pump and used it to ask careful questions. He put a ringing bell inside a jar and pumped the air out, and as the air thinned, the sound faded to nothing, showing that sound needs a medium to travel and cannot cross a vacuum. He showed a candle flame go out as the air was removed, and small animals struggle, learning that both fire and breath depend on something in the air. And he found a clean relationship, that squeezing a gas into half the space doubles its pressure. We still call that Boyle's law. Boyle's work mattered for a reason beyond any single result. He treated the vacuum not as a philosophical puzzle to argue about, but as a tool, a controlled condition you could create and study. Take the air away and watch what changes. That simple method, removing the medium to see what truly depends on it, became one of the most powerful moves in all of science. By the late 1600s, the old horror of the void was finished. Emptiness was no longer forbidden. It could be made, held, weighed by its effects and put to work. But there was a catch hiding in all of this, and it would take another 200 years to surface. Every vacuum Boyle and Guericke made was empty of air. The deeper question remained untouched. Take away the air, the way they had, and something still crosses that empty space without the slightest trouble. Light passes straight through it, and light, it seemed, needed something to travel in. Here is the puzzle that haunted the 1800s. Boyle had shown that sound dies in a vacuum, because sound is a wave in air, and with no air there is nothing to wave. Yet light crosses a vacuum without trouble. Sunlight pours across the empty gulf between the sun and the earth, 93 million miles of near-perfect emptiness, and arrives undimmed. If light is a wave, and through the 1800s the evidence said clearly that it was, then what is doing the waving? A wave, in everything people knew, was a motion of some material. Ocean waves are moving water, sound waves are moving air. Waves on a rope are the rope itself, rising and falling. A wave was not a thing in its own right, but a pattern passing through a medium, and you could not have the pattern without the stuff. So if light was a wave, there had to be a medium for it, some material filling all of space for light to ripple through. Empty space could not be truly empty, because light was crossing it, and a wave needs something to wave. Physicists gave this medium a name. They called it the luminiferous ether, the light-bearing ether, and they granted it whatever properties it needed to do its job. The list grew strange. Light travels extremely fast, and waves move fast through stiff materials, so the ether had to be very stiff, stiffer than steel. Yet the planets sweep through space year after year without slowing, so the ether had to offer no resistance at all, thinner than the faintest gas. It had to fill every corner of the universe, soak through the gaps between the stars and the gaps inside solid glass, and touch everything, while remaining completely invisible and impossible to feel. This was a tall order, a substance that was at once rigid and yielding, everywhere and undetectable. But the alternative seemed unthinkable. A wave with nothing waving was a contradiction. So through most of the 19th century, the finest physicists alive accepted the ether as real. It was the stage on which light performed, the still and universal sea that filled what people had called empty space. The vacuum of the air pump was empty of air, yes, but it was brimful of ether, and that was why light sailed through it. The idea was not foolish. It came from taking the wave nature of light seriously and following it honestly. James Clerk Maxwell, the Scottish physicist whose work we will reach soon, took the ether as real and built his thinking partly around it. Lord Kelvin, one of the towering figures of the age, defended it. The ether was woven into the best physics of its day. To a scientist in 1870, denying the ether would have seemed like denying that water carries ocean waves. And the ether did something the older idea of empty space had never done. It made space into a substance, a real physical medium with properties you could in principle measure, rather than a blank absence. The void was no longer nothing. It was filled, edge to edge, with a stuff that carried light and tied the whole universe together. In a strange way, the ether was the first serious scientific claim that empty space is not empty at all but full, that there is something there. Pour a glass of water and drink half of it. Look at the top half of the glass now, the part with nothing in it. You would call that part empty, and in ordinary life you would be right. We learn the feeling of empty early. A box with nothing in it. A room cleared of furniture. The narrow space between your hand and the wall. In each case, empty means the same simple thing, that the stuff has been taken out and what remains is plain absence, a stage with no actors, a container waiting to be filled. This feeling runs deep and it runs honest. When you wave your hand through the air in a room, you do feel a slight push, because air is a real substance made of molecules. Take the air away and the push goes too. Climb high enough, past the last thin wisp of atmosphere, and you reach a place where almost nothing presses back at all. That is the picture most of us carry of outer space. A vast, cold, silent emptiness. A nothing so complete that sound cannot cross it, because there is no air to carry the sound. For most of human history, the smartest people alive believed this was the end of the matter. Empty was empty, and there was nothing more to say. I want to spend the next couple of hours showing you that this picture, as natural as it feels, is wrong. Not a little wrong around the edges, but wrong at its heart. The space just past your fingertips, the space between the stars, the space inside the atoms that make up your body, is not absence. It is a thing. It has structure. It holds energy. It trembles, very slightly, all the time, and it cannot be made to hold still. By some careful and serious measures, this restless background is the most energetic stuff in the entire universe, far more than all the stars and planets and people combined. That is a strange claim, and I do not want you to simply take it from me. The whole point of what follows is to build it up slowly, so that by the end you can see for yourself why physicists believe it. We will start with the oldest and simplest idea of nothing, and watch it crack again and again, each time someone looked a little closer. Every chapter will rest on the one before it, so you always carry what the next idea needs. Here is the plain question I want to answer. What is really there, inside the nothing? Not the nothing of an empty box which is just air. Not the nothing of a cleared room. The deepest nothing we can make, the true vacuum, the space left behind when every single particle that can be removed has been pulled away. When you scoop out all the matter, all the light, all the air, and you're left with a region of pure space, what is sitting in there? For thousands of years the answer was a single word: nothing. By the end of this video you will understand why the real answer is far richer and far stranger than that. We will meet the people who chipped away at the old picture. A man who tipped a tube of mercury and made the first patch of real emptiness on Earth. Horses that could not pull two metal cups apart. A famous experiment that went looking for an invisible ocean and found bare floor. And the quiet line of thinkers who, piece by piece, realized that emptiness has a temperature, a tension, and a hum. So hold that simple feeling in your mind, the feeling that empty means empty. Honor it, because it served us a long time. Then come with me as we set it gently down. We start where everyone starts, with the very first people who dared to ask whether true emptiness could exist at all. Long before anyone could pump the air from a jar, the question of empty space was an argument among Greek philosophers, and it split them into two camps that could not agree. On one side stood the atomists, Leucippus and his student Democritus, who lived more than 2,000 years ago. They had a bold and beautiful idea. Everything you see, they said, is made of tiny, hard, uncuttable pieces, and they called those pieces atomos, meaning that which cannot be cut. The whole world was just atoms, moving and joining and breaking apart, but atoms need somewhere to move. If the universe were packed solid with matter, with no gaps anywhere, then nothing could ever shift, because there would be no room to shift into. So Democritus and Leucippus insisted on a second thing alongside the atoms. They called it the void. The void was genuine empty space, real nothing, and to them it was just as necessary as the atoms themselves. Without it, motion was impossible. The universe was atoms and void, particles and the emptiness they travelled through, and that was all there was. Against this stood Aristotle, perhaps the most influential thinker in the ancient world, and he found the whole notion of the void unacceptable. Aristotle argued that true empty space could not exist anywhere in nature. His reasoning was careful. He believed that the speed at which a thing moves depends on the thickness of the stuff it moves through. Push your hand through water, and it moves slowly. Push it through air, and it moves faster, because air is thinner. Follow that logic to its end, Aristotle said, and you reach a problem. In a perfect void with nothing at all to slow a thing down, motion would have to be infinitely fast. A stone would cross any gap in no time at all. That seemed absurd to him, and so he concluded that the void simply cannot be. From this came a phrase that echoed for 2,000 years. Nature abhors a vacuum. The Latin form, horror vacui, the horror of the void, became a kind of law. The idea was that nature itself refuses to allow a truly empty region, and rushes to fill any gap before one can form. Suck on a straw, and water climbs up to meet your mouth. Pull a piston back in a tight cylinder, and you feel resistance, as though the space behind it is fighting to stay full. People took these everyday experiences as proof that nature would not tolerate emptiness. Aristotle's view won, and it held for an astonishingly long time. Through the Roman world, through the Middle Ages into the Renaissance, scholars largely agreed that a real vacuum was impossible. The medieval church wove the idea into its picture of the cosmos. The void became not just a mistake, but almost a forbidden thing, a place reason said could not exist. There is something worth noticing in this old fight, because both sides were partly right, and we are still living with the tension between them. The atomists were right that the world is made of tiny pieces moving through space, a picture astonishingly close to the one we hold today. Aristotle was wrong that the void cannot exist, but he was onto something deeper than he knew when he insisted that empty space could never be a simple, harmless nothing. He felt, without the tools to show it, that emptiness was a problem. For now, hold on to the shape of the disagreement. One camp said the void is real and necessary. The other said it is impossible and forbidden. For almost 2,000 years, the question stayed a matter of argument, with no way to settle it, because no one could actually make a vacuum and look at it. That changed in a single afternoon in Italy, when a former student of Galileo filled a glass tube with mercury, turned it over, and watched a small patch of genuine emptiness appear at the top. The man who finally made emptiness was Evangelista Torricelli, an Italian physicist who had served as secretary to Galileo in the last months of the old master's life. Galileo had wondered about a practical puzzle that troubled the well-diggers of Florence. A suction pump could lift water only so high, around 10 meters, and no higher, no matter how hard you worked it. Below that limit, the water rose obediently. Above it, the water simply refused to climb. Aristotle's followers had no good answer. If nature truly abhorred a vacuum, the water should follow the piston up forever, to any height at all. Torricelli, working around 1643, had a different idea, and it was a radical one. Maybe nature did not abhor a vacuum after all. Maybe the water was being pushed up the pipe from below by the weight of the air pressing down on the open pool at the bottom. The atmosphere, the whole ocean of air above us, has weight, and it presses on every surface. That pressure could only lift water so high before it ran out of strength. 10 meters of water was simply as much as the air could hold up. To test this, Torricelli reached for a heavier liquid. Mercury is about 14 times denser than water, so if his idea was right, the air should only be able to support a column about 14 times shorter, less than a meter. He took a glass tube, sealed at one end, and filled it completely with mercury. Then he covered the open end with his thumb, turned the tube upside down, and stood it in a dish of mercury. When he lifted his thumb, the mercury in the tube dropped a little, then stopped. It settled at a height of about 76 centimeters above the dish, and there it stayed, held up by the weight of the air outside. That was striking on its own, but the truly important part sat at the top of the tube. The mercury had fallen away from the sealed top, leaving a gap, and that gap had nothing in it. No air had gotten in, because the tube was sealed and the mercury had filled it completely before it fell. No mercury was there, because the mercury had dropped away. What remained was a space that held no matter at all. Torricelli had made a vacuum, the first deliberate lasting patch of genuine emptiness anyone had ever created. We still call that space at the top of a barometer the Torricellian vacuum. This was a quiet revolution. For 2,000 years the void had been impossible, forbidden, a thing nature would not allow. Now a man in Italy had one sitting in a glass tube on his table and could make another whenever he liked. Aristotle's horror of the void began to look less like a law of nature and more like a habit of thought. Torricelli had built something else too without quite naming it. The height of the mercury column was set by the weight of the air, and the weight of the air changed slightly from day to day with the weather. He had made the first barometer, an instrument that reads the pressure of the atmosphere. He saw the mercury rise and fall on its own and connected it correctly to changes in the air itself. He summed up the deeper picture in a line that has lasted. "We live," he said, "submerged at the bottom of an ocean of air." That single image rearranged how people saw their world. The sky was not a weightless nothing pressing gently overhead. It was a vast, heavy sea, and we were creatures at its floor, holding up a column of mercury with every breath. But Torricelli's vacuum was small, a thumb's width of space at the top of a tube. The next question was irresistible. If you could empty a little space of its air, could you empty a large one? Could you build a machine to pull the air out of a whole vessel, and what would happen if you did? That challenge passed north, to a mayor in Germany with a flair for the dramatic. The man who took emptiness from a tube to a spectacle was Otto von Guericke, the mayor of the German city of Magdeburg and an inventor of real gifts. Around the 1650s he built something the world had never seen, an air pump. It worked a little like a water pump run in reverse, with a piston and valves that let him draw the air out of a sealed container, one stroke at a time, until very little was left inside. For the first time, a person could make a large vacuum on purpose and hold it. Guericke had a showman's instinct, and he understood that a new idea lands hardest when people can see it with their own eyes. So he staged a demonstration that people still talk about. He had 2 large copper hemispheres made, each about 1/2 meter across, with rims that fit together cleanly. He greased the rims, pressed the 2 halves together to form a hollow sphere, and used his pump to suck the air out from inside. Nothing held the halves together but the empty space within, and the air pressing in from without. Then he brought in the horses. Teams of horses were harnessed to each hemisphere and driven to pull in opposite directions, straining to tear the 2 copper cups apart. They could not do it. In the most famous version of the demonstration, given before noblemen and by one account the emperor himself, around 30 horses, 15 to a side, heaved against the sphere and failed. The empty space inside held the halves together with a grip stronger than a team of horses could break. When Guericke opened a valve and let the air rush back in, the hemispheres fell apart at the gentlest touch. What the horses were fighting was not the vacuum reaching out to hold the halves. It was the weight of the atmosphere pushing in. With air inside the sphere, the pressure was balanced, inside pushing out as hard as outside pushed in. Empty the inside and that balance is gone. The full force of the surrounding air presses on the whole outer surface with nothing to push back from within. Across 2 hemispheres half a metre wide that adds up to a load far beyond what the horses could overcome. Guericke had made the pressure of the air visible, turning Torricelli's quiet ocean into a public drama. Word of the air pump spread, and in England it reached a wealthy and brilliant experimenter named Robert Boyle. Boyle, helped by his assistant Robert Hooke, built a better pump and used it to ask careful questions. He put a ringing bell inside a jar and pumped the air out, and as the air thinned, the sound faded to nothing, showing that sound needs a medium and cannot cross a vacuum. He watched a candle flame go out as the air was removed, and small animals struggle, learning that both fire and breath depend on something in the air. And he found a clean relationship, that squeezing a gas into half the space doubles its pressure. We still call that Boyle's law. Boyle's work mattered for a reason beyond any single result. He treated the vacuum not as a philosophical puzzle to argue about, but as a tool, a controlled condition you could create and study. Take the air away and watch what changes. That simple method, removing the medium to see what truly depends on it, became one of the most powerful moves in all of science. By the late 1600s, the old horror of the void was finished. Emptiness was no longer forbidden. It could be made, held, weighed by its effects and put to work. But there was a catch hiding in all of this, and it would take another 200 years to surface. Every vacuum Boyle and Guericke made was empty of air. Take away the air, the way they had, and something still crosses that empty space without the slightest trouble. Light passes straight through it, and light, it seemed, needed something to travel in. Here is the puzzle that haunted the 1800s. Boyle had shown that sound dies in a vacuum, because sound is a wave in air, and with no air there is nothing to carry it. Yet light crosses a vacuum without trouble. Sunlight pours across the empty gulf between the sun and the earth, 93 million miles of near-perfect emptiness, and arrives undimmed. If light is a wave, and through the 1800s the evidence said clearly that it was, then what is doing the waving? A wave, in everything people knew, was a motion of some material. Ocean waves are moving water. Sound waves are moving air. Waves on a rope are the rope itself, rising and falling. A wave was not a thing in its own right, but a pattern passing through a medium, and you could not have the pattern without the stuff. So if light was a wave, there had to be a medium for it, some material filling all of space for light to ripple through. Empty space could not be truly empty, because light was crossing it, and a wave needs something to wave. Physicists gave this medium a name. They called it the luminiferous ether, the light-bearing ether, and they granted it whatever properties it needed to do its job. The list grew strange. Light travels extremely fast, and waves move fast through stiff materials, so the ether had to be very stiff, stiffer than steel. Yet the planets sweep through space year after year without slowing, so the ether had to offer no resistance at all, thinner than the faintest gas. It had to fill every corner of the universe, soak through the gaps between the stars and the gaps inside solid glass, and touch everything, while remaining completely invisible and impossible to feel. This was a tall order, a substance that was at once rigid and yielding, everywhere and undetectable. But the alternative seemed unthinkable. A wave with nothing waving was a contradiction. So through most of the 19th century, the finest physicists alive accepted the ether as real. It was the stage on which light performed, the still and universal sea that filled what people had called empty space. The vacuum of the air pump was empty of air, yes, but it was brimful of ether, and that was why light sailed through it. The idea was not foolish. It came from taking the wave nature of light seriously and following it honestly. Lord Kelvin, one of the towering figures of the age, defended the ether. It was woven into the best physics of its day. To a scientist in 1870, denying the ether would have seemed like denying that water carries ocean waves. And the ether did something the older idea of empty space had never done. It made space into a substance, a real physical medium with properties you could in principle measure, rather than a blank absence. The void was no longer nothing. It was filled, edge to edge, with a stuff that carried light and tied the whole universe together. In a strange way, the ether was the first serious scientific claim that empty space is not empty at all but full, that there is genuinely something there. But while many physicists pictured the ether as a kind of cosmic jelly, a quieter and deeper idea was taking shape in England, in the hands of a bookbinder's apprentice who could barely do mathematics. He would propose that space itself holds something real, not a mechanical substance but a field, an influence spread through every point of empty space. And a Scottish physicist would later turn that vision into a set of equations so powerful that they still describe light today. The bookbinder's apprentice was Michael Faraday, one of the greatest experimenters who ever lived, and one of the most unlikely. He came from a poor family, had almost no formal schooling, and learned his science by reading the books he was binding. He never mastered the heavy mathematics of his day. What he had instead was an extraordinary physical imagination, an ability to see in his mind what was happening in the space around magnets and charged objects, sprinkle iron filings on a sheet of paper and hold a magnet underneath. The filings arrange themselves into graceful curving lines, looping from one pole of the magnet to the other. You've seen this, or something like it. Most people of Faraday's time looked at those lines and saw a pretty pattern, a side effect of the magnet's hidden power. Faraday looked at them and saw something real. He became convinced that the lines were not decoration but the very thing itself, that the space around the magnet was genuinely filled with a state of strain, a pattern of influence reaching out into the emptiness. He called these lines of force, and he came to believe that the field, this condition of the space, was where the action truly lived. This was a deep shift. Before Faraday, most physicists thought of forces as acting at a distance, one magnet reaching invisibly across a gap to tug another, with the empty space in between playing no part at all. Faraday reversed it. The space in between was everything. A magnet does not reach across emptiness to grab a nail. The magnet fills the surrounding space with a field, and the nail responds to the field right where the nail sits. The influence travels through the space, point by point, and the empty region is the medium that carries it. Once again, empty space was being handed a job to do. Faraday could see this, but he could not write it down in the language of mathematics. That task fell to James Clerk Maxwell, a Scottish physicist of rare power, who took Faraday's pictures seriously when many others dismissed them as the fancies of a man who could not do the equations. Maxwell translated the lines of force into precise mathematical law, and in doing so he pulled together everything then known about electricity and magnetism into a single framework, a set of relationships we now call Maxwell's equations. Then came the moment that changed physics. Maxwell's equations described how a changing electric field creates a magnetic field, and how a changing magnetic field creates an electric field. He realized the two could feed each other and travel together, an electric field giving rise to a magnetic field, giving rise to an electric field, leapfrogging through space as a self-sustaining wave. When he calculated how fast such a wave would move, the number that came out matched the measured speed of light. The match was no coincidence. Light, Maxwell concluded, simply as a wave in the electric and magnetic fields, a ripple in the very fields Faraday had imagined around magnets and charges. This was one of the great unifications in the history of science. Light, electricity, and magnetism were three faces of one thing, the electromagnetic field. And the field, this real and structured presence, filled all of space. Maxwell himself still pictured the field as a state of the ether, a strain in that universal medium. The field and the ether were, for him, bound together. So by the late 1800s, empty space carried not one passenger but two: the ether, the supposed medium, and the electromagnetic field that rippled through it as light. The picture felt complete. All that remained was to catch the ether itself, to feel the wind of it as the earth swept through. Two Americans built an instrument of breathtaking precision to do exactly that, and what they found pulled the floor out from under the whole construction. The two Americans were Albert Michelson and Edward Morley, and in 1887 they performed what may be the most famous failed experiment in all of physics. Their logic was clean. If space is filled with a still ether, and the Earth is hurtling around the Sun at about 30 kilometers per second, then the Earth must be moving through the ether. From the Earth's point of view, that is an ether wind, a steady current of ether streaming past, the way a still day feels windy when you ride a bicycle through it. Catch that wind, measure its speed, and the ether is proven. To catch it, they used light itself. Michelson had invented an instrument of exquisite sensitivity, now called an interferometer. It takes a single beam of light, splits it in two with a half-silvered mirror, and sends the two halves down two paths at right angles to each other. Each half runs out to a mirror, bounces back, and the two beams are recombined. When light waves overlap, they produce a pattern of bright and dark bands, and that pattern shifts if one beam takes even slightly longer to make its trip than the other. Here was the idea. If there is an ether wind, then light moving along the wind and light moving across it should travel at slightly different speeds, just as a swimmer crossing a river and a swimmer fighting upstream take different times. The two beams in the interferometer should fall out of step, and the bands of light should shift by a measurable amount. By turning the whole apparatus, they could swing the arms into and out of the ether wind and watch the pattern move. To kill outside vibration, they floated the entire instrument on a pool of liquid mercury so it could be rotated smoothly, and they took readings as it slowly turned. The expected shift was small but well within reach of Michelson's instrument, which could detect differences far finer than what the ether wind should produce. They ran the experiment carefully, at different times of day and different times of year, so that the Earth's motion would point in every direction relative to the apparatus. They knew what a positive result would look like. The bands would creep one way as the arms turned into the wind, and back as they turned out of it. The bands did not move. Not in the way the ether predicted, not at any time of day, not in any season. Within the precision of the instrument, the speed of light was exactly the same in every direction, whether the beam ran along the Earth's motion or across it. There was no ether wind. The current of ether that should have been streaming past the Earth left no trace at all. This was a genuine shock, because the experiment was good and the prediction was clear. The result was checked and repeated by Michelson and Morley and by others with ever greater care, and the answer held. Light moved at the same speed in every direction, as though the Earth were standing perfectly still in the ether, which made no sense, since the Earth plainly moves around the Sun. Physicists tried hard to save the ether. Some proposed that moving objects shrink slightly along their direction of travel, by just the right amount to hide the wind. That idea, strange as it sounds, turned out to contain a seed of truth, but as a patch on the ether it felt forced, an excuse invented only to explain away a missing result. The deeper trouble was simple and devastating. The whole reason for the ether had been to carry light, to be the medium a wave needs. Now the most careful search ever made could find no sign of it. The medium that was supposed to fill all of empty space, the substance that made the vacuum not empty, had failed to appear when called. Empty space had quietly refused to hold the thing physics had placed in it. Resolving that required a mind willing to throw the ether away entirely and keep only what the experiments truly demanded. That mind belonged to Albert Einstein, and in 1905, working as a clerk in a Swiss patent office, he published the paper that became the special theory of relativity. Einstein took the failure of the ether search and turned it from an embarrassment into a foundation. Instead of asking how the ether could hide its wind, he asked what the world would have to be like if there were no ether wind to find, because there was no ether at all. He built his theory on two simple statements taken as bedrock. The first is that the laws of physics are the same for everyone moving steadily, with no special privileged point of view, no one truly at rest while others move. The second is the strange one, the one Michelson and Morley had forced onto the table. The speed of light in empty space is the same for every observer, no matter how fast they are moving toward the light or away from it. Run toward a beam of light, and it still approaches you at the same speed as if you stood still. That defies all everyday sense, the way nothing else in our experience behaves, and yet it is what the experiments showed. From those two statements, taken seriously and followed without flinching, Einstein drew conclusions that reshaped our picture of reality. Moving clocks run slow. Moving objects shorten along their direction of travel. Two events that look simultaneous to one person happen at different times for another. Space and time, which everyone had treated as a fixed and separate stage, turned out to be flexible, woven together into a single fabric that stretches and tilts depending on how you move. The shrinking that others had bolted onto the ether as a desperate patch fell out of Einstein's theory naturally, as a real feature of space and time, with no ether needed at all, and the ether, in Einstein's hands, simply vanished. It was not disproven so much as made unnecessary. Light needs no medium. Light is its own thing, a wave in the electromagnetic field that requires nothing to carry it. The whole reason for the ether had been to be that carrier, and once you no longer needed a carrier, the ether had no work left to do. Einstein cleared the stage of the cosmic jelly that physics had filled it with for a century. It would be easy to think this brought us right back to the old simple emptiness, space's plain absence, the void of Aristotle's enemies finally triumphant. But that is not what happened, and the difference is the heart of this whole story. Einstein removed the ether, but he did not empty space of structure. Quite the opposite. In his theory, space and time form a real physical fabric with measurable properties. It has a geometry. Distances and durations are woven into it. It can be measured, and as Einstein would show a decade later in his theory of gravity, it can even bend and curve in the presence of matter and energy. So the stage was cleared of one tenant only to reveal that the stage itself was alive. Space was not the ether, but it was not nothing either. It had become something subtler, a fabric with its own real properties, a structure that does things. Einstein had taken away the medium and left behind a space that was still somehow a physical thing. And there was a passenger Einstein never asked to leave. The electromagnetic field, Faraday and Maxwell's field, did not depend on the ether the way light had been thought to. Strip the ether away, and the field is still there, spread through every point of space, perfectly real, carrying light across the void on its own. The ether was gone. The field remained. And the field, it would turn out, was about to become stranger than anyone holding it had yet guessed. So let us be careful about what was left standing after Einstein. The ether was gone, dismissed as a medium no experiment could find and no theory needed. But the electromagnetic field stayed. The field had always been a slightly different idea from the ether, even though Maxwell had tangled the two together. The ether was imagined as a material, a substance like a very thin, very stiff jelly. The field was something else, a condition of space itself, a set of numbers attached to every point, telling a charged particle which way it would be pushed and how hard. Hold that distinction, because it matters. When you bring a charged comb near a scrap of paper, the paper jumps to it. The old idea of action at a distance said the comb reached across the gap and grabbed the paper directly. The field idea says something different. The comb fills the surrounding space with an electric field, a real condition present at every point in that region, and the paper feels the field right where the paper sits. The field is the middleman, and it lives in the space between. Take away the ether, and the field does not fall with it, because the field was never the ether. The field is its own thing. You can see why this is more than a word game. The field carries energy. A radio wave crossing a room, a beam of sunlight crossing the solar system. These are real ripples in the electromagnetic field, and they carry real energy from one place to another. That energy is in the field, in the space itself, not in any material medium. When sunlight warms your face, energy has travelled 93 million miles through near-empty space and landed on your skin, carried the whole way by the field. There was no ether to ferry it. The field did the work alone. This forces a quiet but profound conclusion. Empty space, the vacuum, is the home of the electromagnetic field. Even when you remove every particle, every speck of matter, every atom of air, the field is still defined at every point in that region. Usually in truly empty space, the field is simply zero everywhere. No push, no pull, nothing happening. But zero is not the same as absent. The field is still there, present and defined, just resting at the value zero. The way a still pond is still water even when its surface is flat and unmoving. That image of the still pond is worth holding on to, because it is about to become the key to everything that follows. Picture the electromagnetic field across all of empty space as the surface of a perfectly calm lake at night, flat and dark and motionless. In the world of classical physics, the physics of Maxwell and Einstein, that calm is allowed to be perfect. The field can sit at exactly zero, everywhere, forever, with no ripple at all. A truly empty vacuum would be a field lying perfectly flat and perfectly still, holding exactly zero energy. That was the picture as the 1900s opened. It is a clean picture, and it nearly survived. The vacuum is space with the field in it, and in empty space the field rests at zero, holding no energy, making no sound. Empty space had structure. Yes, it held a field, but the field could be silent, and silence felt like a kind of emptiness after all. But that calm lake was about to be disturbed, not by anything you could remove or add, but by a new and unsettling discovery about how nature works at its smallest scale. The trouble began somewhere that seemed to have nothing to do with empty space at all, in the puzzle of why a hot piece of iron glows the colour it does. The answer to that small puzzle would forbid the field from ever lying perfectly flat, and the calm lake would begin, very faintly, to tremble. The trouble began with a glowing object. Heat a bar of iron in a forge and it changes colour, from dull red to bright orange to a fierce yellow-white as it gets hotter. Every warm thing gives off light in this way, even your own body, glowing faintly in colours too far into the infrared for your eyes to see. By the end of the 1800s, physicists wanted to explain exactly how much light of each colour a warm object should give off, and they had every reason to think the answer was within reach. It was not. Their best theory gave an answer that was not just wrong, but absurd. The theory said that a hot object should pour out more and more energy at shorter and shorter wavelengths, toward the blue and the violet and beyond, without limit. Add up the energy across all the colours, and the total came out infinite. Every warm thing, by this reasoning, should blaze with an endless flood of high-frequency light. A cup of warm tea should blind you with violet and bury you in invisible radiation past it. Plainly nothing of the kind happens. The failure was so glaring it earned a dramatic name, the ultraviolet catastrophe. The man who found the way out was Max Planck, a careful and conservative German physicist who did not enjoy overturning things. In 1900, almost against his own instincts, Planck found that he could get the right answer, the answer that matched what warm objects actually do, only by making one strange assumption. He had to suppose that energy is not handed out smoothly, in any amount you like, but only in discrete lumps, small fixed packets. A warm object could not emit just any quantity of light energy. It could emit 1 packet, or 2 packets, or 3, but never a packet and a half. The size of each packet depends on the colour of the light, the frequency of the wave. Higher frequency light toward the blue and violet comes in bigger packets, and here is where the catastrophe is tamed. To emit high frequency light, an object must cough up one of those large packets all at once, and at ordinary temperatures it rarely has enough energy on hand to do so. The high frequencies are not impossible, just expensive, and so they are rare rather than infinite. The flood is stopped at the source. Planck's lumps cut off the runaway, and his formula matched the real glow of warm things exactly. Planck called the size of these packets a quantum, from the Latin for how much, and the rule connecting a packet's energy to its frequency involves a new constant of nature, an incredibly tiny number now called Planck's constant. It is one of the smallest important numbers in all of physics, which is why the lumpiness of energy stays hidden in everyday life. The packets are so small that ordinary light looks perfectly smooth, the way a beach looks like a continuous surface until you kneel down and see the separate grains of sand. Energy, Planck had found, comes in grains. Planck himself thought this was a mathematical trick, a strange bookkeeping rule that happened to work, not a true statement about reality. He spent years hoping someone would find a way to get the right answer without the lumps. No one did. The lumpiness was real. Energy genuinely comes in packets, and that single fact would grow into the whole of quantum physics, the theory of the very small, which behaves nothing like the smooth, continuous world our senses report. For our story, Planck's quantum carries a hidden consequence, one that took years to surface. If a field like the electromagnetic field can only hold energy in discrete packets, then the field is a more delicate, more particular thing than Maxwell ever imagined. It cannot do just anything. Its energy is constrained, counted, grainy. And a field made of grains, it turns out, faces a problem when you ask it to lie perfectly flat and perfectly still. That problem has a name and a discoverer, and it is the moment our calm lake is forbidden, once and for all, from ever being truly calm. The discovery that forbade perfect stillness came from Werner Heisenberg, a young German physicist, who in 1927 put forward what we now call the uncertainty principle. It is one of the strangest and most solid results in all of science, and it sits at the very heart of why empty space cannot be empty. The principle says, in plain terms, that there are certain pairs of properties in nature that cannot both be pinned down at the same time. The more precisely you fix one, the more the other goes blurry. This is not a limit of our instruments. It is a limit built into the way the world is. The most famous pair is position and motion. You cannot know exactly where a particle is and exactly how it is moving both at once. Pin down its location with perfect precision, and its motion becomes completely undefined, wild and unknowable. Pin down its motion perfectly and its location smears out across all of space. Nature simply does not allow both to have sharp values together. An electron does not possess a definite position and a definite speed waiting to be measured. The values are not hidden from us. They are not there to be had. This sounds like a rule about particles, about little specks of matter, and at first that is how it was understood. But the uncertainty principle reaches further, and this is the step that changes everything for empty space. It applies not only to particles but to fields. For a field, the matching pair of properties is the strength of the field at a point, and how fast that strength is changing, and the principle forbids both from being exactly zero at the same time. Sit with that, because it is the whole game. To have a truly empty vacuum the old way, you would need the electromagnetic field to be exactly zero everywhere, and to be perfectly still, not changing at all. Field value, 0. Rate of change, 0. Both sharp, both exact, both nothing. That is precisely the calm lake we pictured, the surface flat and motionless forever. And that is exactly what the uncertainty principle says you cannot have. You cannot fix the field at 0 and fix its change at 0 at the same time. Demand that the field sit perfectly at 0 and its rate of change blurs out, which means the field is moving, twitching, refusing to stay put. The perfect stillness is not merely hard to achieve, it is forbidden by the deepest law of the quantum world. Here is an everyday handle, imperfect but useful. Imagine trying to balance a pencil perfectly on its sharpened point so that it stands exactly upright and exactly motionless. In the ordinary world, you could imagine getting it just right if your hands were steady enough. The quantum world says no. To stand exactly upright, the pencil would have to have an exactly known position and an exactly zero motion, both at once and that pairing is not allowed. There is always a residual wobble built in, a minimum trembling that cannot be removed by any amount of care, because removing it would violate the principle itself. So the calm lake of the vacuum can never be truly calm. The electromagnetic field, told it must hold zero energy and lie perfectly flat, cannot obey. It is forced to keep a faint, ceaseless tremble, a built-in jitter that no cooling, no emptying, no careful preparation can ever take away. This restless minimum is not energy we put into the field. It is energy the field cannot get rid of, the lowest it is allowed to go, and that lowest is not zero. That irreducible trembling, the motion left in the field, when every removable scrap of energy has already been taken out, has a name. Physicists call it zero-point energy, and it is the first real answer to our question about what sits inside the nothing. Zero-point energy is the energy that stays behind when everything that can be taken away has already been taken away. Cool a system to the lowest temperature allowed, absolute zero, the point where all ordinary heat motion stops. Remove every particle you can remove, drain off every scrap of energy the laws permit you to drain. And still, the quantum world tells you a faint motion remains. It is the floor beneath which nothing can be pushed, the residue the uncertainty principle leaves behind. The name says it plainly. It is the energy left at the 0 point, the energy of a system in its lowest possible state, which is not nothing. You can meet this idea in something simpler than empty space, in a single atom. In an ordinary solid, the atoms are always jiggling, and the colder you make the solid, the less they jiggle. Common sense says that at absolute zero the jiggling should stop entirely, every atom frozen perfectly in place. But it does not stop. Even at absolute zero, the atoms keep a small, irreducible quiver, because an atom frozen perfectly still would have an exact position and exactly zero motion, and that pairing is forbidden. Helium shows this dramatically. Cool helium down and it refuses to freeze solid under its own pressure, no matter how cold you make it, because the 0 point jiggle of its atoms is strong enough to keep the liquid from ever settling into a rigid crystal. The trembling holds it liquid all the way down. Now carry that same idea back to the electromagnetic field in empty space. The field we have seen cannot lie perfectly flat. At every point in the vacuum it keeps its faint, forbidden tremble, its 0 point motion. And a tremble is energy. So empty space, the true vacuum with every particle removed, is not at zero energy. It holds the summed up 0 point energy of the field, a restless background that hums along at the lowest level nature permits, which is still above nothing. Picture again the lake at night, but now see it truly. Not a sheet of glass, perfectly flat, but a surface that shivers everywhere with tiny ripples, a fine, endless texture of motion that never settles, even when no wind blows and no stone is thrown. That shivering surface is the vacuum. It is what is left when you take everything out. The ripples are not waves you can ride or use. They are the irreducible minimum, the field doing the least it is allowed to do, which is not nothing and can never be nothing. This restless ground has a strange and slippery feature. When you try to add up how much 0 point energy is really there, in every patch of empty space, across every possible ripple the field can hold, the total grows enormous, and in the simplest accounting it runs to infinity. Every point in space contributes its tremble, and there are endless points, and endlessly fine ripples at each one. That runaway total would haunt physics for decades, and we will face it squarely later because it grows into one of the deepest puzzles in all of science. For now, hold the gentler and surer truth. The vacuum is not still. The field that fills all of empty space carries a built-in trembling that cannot be removed, a 0 point energy that is the true floor of reality. The old calm lake is gone for good. What sits inside the nothing is, at the very least, this faint and ceaseless hum. And once you accept a trembling field, a new possibility opens, one that sounds like fantasy but follows directly from the physics. If the field is always faintly stirring, never quite at rest, Then in that stirring, particles themselves can flicker into being and vanish again. To see how, we turn to a physicist who was trying only to make one equation behave, and who stumbled instead into a mirror world hiding inside the vacuum. The physicist was Paul Dirac, an Englishman of famously few words and ferocious mathematical power, and in 1928 he was chasing a clean goal. Quantum theory described the electron, and Einstein's relativity described how anything fast must behave. Dirac wanted one equation that obeyed both at once, a description of the electron that worked even when the electron moved near the speed of light. He found it. The Dirac equation is one of the most beautiful results in physics, elegant and spare, and it described the electron perfectly, even predicting a subtle property of the electron's magnetism that matched experiment with stunning accuracy. But the equation came with a strange gift Dirac had not asked for. When he solved it, it gave him not one kind of answer but two. Alongside the ordinary electron with its familiar negative charge, the mathematics insisted on a second solution, a particle just like the electron but with the opposite charge, positive instead of negative. The equation would not let him throw this second solution away. It was built into the structure, as real as the first. At first this looked like an embarrassment. There was no known particle that was a positive twin of the electron. Dirac wrestled with the problem and offered a bold and peculiar picture to make sense of it. Imagine, he said, that what we call empty space is not empty at all, but is completely filled, everywhere, with a vast sea of electrons sitting in negative energy states, packed so full that no ordinary electron can fall into them, because every seat is already taken. We do not notice this infinite sea precisely because it is everywhere and uniform, the way a fish might not notice water. This came to be called the Dirac Sea, and in it the vacuum became a brimming crowded thing, a filled ocean we mistake for emptiness. In this picture, the positive twin was a hole. Knock one electron out of the negative energy sea, and you leave behind a gap, a missing negative charge, which behaves exactly like a positive particle. The hole moves, carries charge, acts in every way like a real particle, yet it is really an absence in the filled vacuum, a bubble in the sea. It was a strange and heavy idea, an infinite ocean of hidden electrons filling all of space just to explain one extra solution. The full picture was eventually cleaned up, and we no longer need the literal sea. But the core prediction was breathtaking, and it was right. There should exist a particle with the same mass as the electron and the opposite charge, a mirror image partner. We call it the positron, and more broadly we call this kind of mirror matter antimatter. In 1932, just a few years after Dirac's equation, the American physicist Carl Anderson found the positron in the tracks left by cosmic rays striking his detector, a particle curving the wrong way in a magnetic field, exactly as Dirac's mathematics had demanded. The mirror world was real. Dirac had pulled antimatter out of pure equations, predicting a whole category of particles before anyone had seen one. And whatever we make of his literal filled sea, he had done something lasting to our picture of the vacuum. He had shown that empty space and the existence of particles are tangled together, that the vacuum is not a passive backdrop but something with hidden structure, capable of holding or hiding or giving up particles and their mirror twins. That tangling points straight at the next idea. If a particle and its antiparticle are mirror partners that can be created together, and the vacuum is a trembling energetic field, then perhaps the vacuum can make such pairs on its own, briefly, out of its own restless energy. That is exactly what happens, and it is one of the strangest truths in physics. Empty space is constantly flickering with particles that appear, live for the briefest instant, and vanish. These flickering particles are called virtual particles, and they are the vacuum's most startling trick. The idea grows directly from everything we have built. The vacuum holds a trembling field with 0-point energy. The uncertainty principle forbids that field from ever being perfectly still. And one more piece of the uncertainty principle now comes into play, a version that links energy and time. Just as you cannot pin down position and motion together, you cannot pin down energy over a very short interval with perfect sharpness. For a brief enough flash of time, the energy of a system is fundamentally fuzzy, undefined, free to wander from its average. That fuzziness opens a loophole, and nature uses it constantly. Over a long stretch of time, energy is strictly conserved, never created from nothing, never destroyed. But over a short enough instant, the books do not have to balance exactly. The vacuum can borrow a little energy from itself, use it to bring a pair of particles into being, a particle and its antiparticle together, and then pay the energy back by letting them collide and vanish, all within a window so brief that the universe never registers the loan. Borrow, create, annihilate, repay, faster than any clock could catch. So the vacuum is not merely trembling, it is boiling, in a quiet and constant way. Everywhere, at every instant, pairs of particles are winking into existence and winking back out, electrons and positrons and many other kinds, appearing for a flicker and annihilating before the debt comes due. They are called virtual because they never last long enough to be caught and held like an ordinary particle. You cannot put one in a box. They live on borrowed time and borrowed energy, and they vanish before the loan is called in. A fair handle for this is a still pot of water held right at the edge of boiling, where tiny bubbles form and collapse on the surface faster than you can track them, never quite breaking free. The vacuum is like that surface, fizzing with pairs that rise and fall back. But the comparison has a limit worth naming. Real bubbles are made of something already present, water becoming vapour. The vacuum's pairs are made from the field's own restless energy, conjured from the uncertainty of the void itself, and they are matter and antimatter, not a change of phase. The bubbles in the pot are warmed by a flame. The bubbles in the vacuum are warmed by the uncertainty principle. Now, it would be fair to be suspicious here. This is a strange story. Particles flickering in and out of nothing, and you would be right to ask whether it is real physics or just a vivid way of talking, a picture with no teeth. That is the honest and important question, and physics has a clear answer. The constant froth of virtual particles is not a metaphor. It leaves real, measurable marks on the world, fingerprints that should not be there unless the vacuum truly seethes. If empty space were the old calm nothing, those marks would be absent. They are not absent. They have been measured, again and again, to extraordinary precision. The vacuum's froth nudges the light an atom gives off. It changes how strongly two charges attract. It pulls metal plates together across an empty gap. Each of these is a place where the seething of empty space steps out of theory and into the laboratory, where you can point an instrument at the nothing and watch it do something. Over the next chapters, we'll visit these fingerprints one by one, starting with the most delicate of them, a tiny shift in the light of hydrogen that first proved the restless vacuum was real. It is small, a whisper of a measurement, and it changed physics completely. The fingerprint was found in hydrogen, the simplest atom there is, a single electron bound to a single proton. By the 1940s, physicists understood hydrogen extraordinarily well. The electron can sit in various energy levels around the proton, like rungs on a ladder, and the theory of the day, Dirac's beautiful equation, predicted exactly where those rungs should be. In particular, it said that two specific states of the electron should have precisely the same energy, sitting at exactly the same height on the ladder. The prediction was clean and definite. Those two levels should line up perfectly. In 1947, the American physicist Willis Lamb, working with his colleague Robert Rutherford, decided to check this with great care, using the precise microwave techniques that had been sharpened during the war. They measured the two hydrogen states that were supposed to coincide. They did not coincide. One of the levels was nudged very slightly away from the other, shifted by a tiny amount that Dirac's equation said should not be there at all. The gap was minuscule, but Lamb's measurement was good enough to see it clearly and to measure its size. We now call it the Lamb shift, and that small discrepancy turned out to be a direct window into the seething vacuum. Why should two levels that theory placed together be pushed apart? The answer is the restless vacuum. The electron in a hydrogen atom is not sitting in calm, empty space. It sits in the froth, surrounded everywhere by the trembling electromagnetic field and its constant flicker of virtual particles. That froth jostles the electron, nudging it this way and that with countless tiny kicks, so that the electron does not follow the smooth path Dirac's equation assumed. It is smeared out a little, jittering in the vacuum's churn, like a buoy bobbing on choppy water rather than resting on a flat pond. That faint jitter changes the electron's energy by a hair, and it changes it differently for the two states, because they hold the electron at different average distances from the proton. The result is that the two levels, which should have matched, are split apart by the exact small amount Lamb measured. This was the moment the seething vacuum stopped being a picture and became a fact. The Lamb shift could not be explained by an atom sitting in true emptiness. It could only be explained if empty space around the electron was alive with virtual particles, pushing on the electron and shifting its energy. The size of the shift matched what that churning vacuum should produce. Here was a number measured in a laboratory that existed only because empty space is not empty. You could point your instrument at a hydrogen atom and read off, in the displacement of a single line, the touch of the restless void. The effect is almost unimaginably gentle. The shift is a tiny fraction of the energies involved, a faint detuning of one note in the atom's spectrum, and yet it is unmistakably there, and it is exactly the size the trembling vacuum predicts. Lamb received the Nobel Prize for finding it, because that whisper of a measurement settled something enormous. The vacuum is real, and it touches matter, and its touch can be weighed. But the Lamb shift also exposed a deep problem, the same one that had haunted the zero-point energy. When physicists tried to calculate the shift from first principles, by adding up the effect of all those virtual particles, the sum blew up to infinity, just as the vacuum's total energy had. The froth, taken at face value, gave nonsense, an endless number where a small finite one was needed. To turn the theory into something that could predict Lamb's measured value, physicists had to learn a difficult and controversial new art, a way of handling the infinities of the vacuum without being destroyed by them. The art was called renormalization, and the people who built it shared the 1965 Nobel Prize in Physics, the American Richard Feynman, the American Julian Schwinger, and the Japanese physicist Shinichiro Tomonaga, who had worked out much of it independently in wartime isolation. Together their work completed the theory of how light and matter interact, a theory called quantum electrodynamics, usually shortened to QED. It is, by many measures, the most precisely tested theory in the history of science, and it is built on taming the infinities of the vacuum. The problem they faced was the one the Lamb shift had laid bare. The vacuum seethes with virtual particles, and when you try to add up their effects on anything, the electron's energy, the electron's charge, the shift of a hydrogen level, the sums run to infinity. Take the electron's own electric field, surrounded by its own cloud of virtual particles, and ask how much energy is tangled up there, and the honest calculation gives an infinite answer. Plainly, the electron does not have infinite energy. Something in the naive calculation was being read too literally. The insight behind renormalization is subtle, and it troubled even the people who invented it. The infinities, they realized, hide inside quantities we never actually measure on their own. We never see the bare electron stripped of its cloud of virtual particles. We can only ever measure the real electron as it comes to us, already dressed in its froth, already wrapped in the vacuum's churn. The mass we measure and the charge we measure are the dressed values, the electron together with its cloud, not the bare numbers buried in the equations. So the trick is this: wherever an infinity appears in the bare quantities, you fold it into the relationship between the bare value and the measured value, and you anchor the theory to the real, finite numbers you actually weigh in the laboratory, the measured mass and the measured charge of the electron. The infinities cancel between the bare quantities and the corrections, leaving finite, sensible predictions for everything else. It is, in plain terms, a careful and consistent bookkeeping that subtracts the endless parts by tying the theory to real measurements, so that what remains is the small, true difference you can actually test. Feynman, who hated anything murky, was uneasy about it, and called the procedure a kind of shell game, suspecting that one day a deeper theory would justify it more cleanly. And yet it worked, and worked beyond all reasonable hope. Feynman also gave physics a gift that made the whole calculation manageable. His famous diagrams, simple line drawings of particles meeting, exchanging virtual particles, and parting, each diagram standing for a precise piece of the calculation. The Feynman diagram turned a forbidding tangle of mathematics into something you could almost sketch on a napkin, and it became the universal language of particle physics. The payoff is staggering. QED predicts a particular property of the electron's magnetism, and that prediction agrees with experiment to about 12 decimal places, an accuracy so fine it is like measuring the distance across a continent and being off by less than the width of a human hair. That agreement rests entirely on taking the seething vacuum seriously, on counting its virtual particles honestly and handling their infinities with care. The vacuum is not a nuisance to be ignored. It is woven into the most accurate prediction humanity has ever made. We have now reached a turning point. The restless vacuum is no longer a strange idea, but a measured, calculated, precisely tested fact. From here, we stop asking whether empty space does anything and start asking what else it does. The next answer is the most tangible of all, a force you can feel, two plates drawn together by nothing but the emptiness between them. The force was predicted in 1948 by a Dutch physicist named Casimir, who was working at the Philips Research Laboratory in the Netherlands, thinking about why certain liquids behaved the way they did. He came at the vacuum from a clean and daring angle. If empty space is filled with the trembling electromagnetic field, with all its zero-point ripples, then that field is present everywhere, holding every possible wavelength at once, every size of ripple the space can contain. Now, Casimir asked, what happens if you place two flat metal plates very close together, facing each other, and let the vacuum fill the gap between them as well as the room outside? Here is the heart of it. Outside the plates, in the open, the field can hold ripples of every size, long and short, with no restriction. But in the narrow gap between the plates, the field is fenced in. A metal plate forces the electric field to behave in a particular way at its surface, and that means only certain ripples fit cleanly in the gap, the ones whose size divides evenly into the space between the plates, the way a guitar string of a fixed length can only ring at certain notes. The very long ripples, the ones too big to fit, are shut out of the gap, so the gap holds fewer kinds of vacuum ripple than the open space outside. Fewer ripples inside means less zero-point energy packed into the gap than into an equal slice of open space, and the vacuum, like everything in physics, prefers to sit at the lowest energy it can reach. With more crowding ripples pushing from outside than from the thinned-out inside, the plates are pressed together. Empty space itself squeezes them, not because anything material is pushing, but because the vacuum outside holds more trembling than the vacuum between. The plates are nudged together by a difference in the energy of nothing. This is the Casimir effect, and pause on how strange it is. Two ordinary metal plates, uncharged, with nothing between them, not even air, are drawn toward each other by the structure of the vacuum. The force comes from the simple fact that the plates change which vacuum ripples are allowed nearby, and that change has a real, mechanical consequence you could in principle feel. It is the seething of empty space, reaching out and pressing on solid metal. The force is faint, and it hides easily, which is why Casimir's prediction sat largely untested for decades. It only becomes noticeable when the plates are extraordinarily close, a fraction of the width of a human hair apart. At that range, the push grows quickly, getting stronger the closer the plates come, rising steeply as the gap narrows. At separations of a few millionths of a meter, it is small but real. At separations 100 times smaller, it can rival the ordinary pressures engineers worry about. In the tiny machines we now build at the scale of microchips, the Casimir force is a genuine engineering concern, capable of pulling delicate parts together and sticking them fast, a ghost from quantum theory making trouble in a factory. Notice what Casimir had done. The zero-point energy of the vacuum had seemed, until then, like something you could never get a handle on. A background hum with no obvious effect, perhaps even just a bookkeeping quantity. Casimir found a way to make that hum do mechanical work, to turn the trembling of empty space into a measurable force between real objects. He took the most abstract feature of the vacuum and gave it a handle you could, in principle, push against. But a prediction, however beautiful, is only as good as the measurement that confirms it. For nearly 50 years, the Casimir force remained mostly a theorist's delight, too delicate to pin down cleanly. The question of whether the vacuum truly pushes, by exactly the amount the theory said, waited for an experimenter patient enough to weigh a force made of emptiness. That experimenter was Steve Lamoureux, an American physicist, who in 1997, working at the University of Washington, finally measured the Casimir force cleanly enough to settle the matter. Casimir had predicted it half a century earlier, and others had tried over the years, but the measurement is brutally hard, and the early attempts could only show rough agreement, enough to suggest the force was there, but not enough to pin it to the theory. Lamoureux brought the precision that turned a strong suspicion into a confirmed fact. The difficulty is worth feeling, because it shows how delicate this force from nothing really is. To see the Casimir push, you must bring two surfaces within a fraction of a hair's width of each other and hold them there with exquisite steadiness, while measuring a force far weaker than the weight of a single grain of sand. Any speck of dust between the surfaces ruins everything. Any leftover electric charge on the metal creates its own pull that swamps the effect you are hunting. Any vibration from a passing truck or a footstep in the hall shakes the whole measurement apart. You're trying to weigh the pressure of empty space against a world full of louder forces. Lamoureux solved this with a clever instrument built around a torsion pendulum, a delicate balance that twists in response to the faintest sideways push. He used a flat plate and a curved lens surface coated in metal, rather than two flat plates, because keeping two flat plates perfectly parallel at such tiny separations is nearly impossible, while a curved surface near a flat one sidesteps that problem. As he brought the surfaces close, the Casimir force tugged the pendulum, twisting it by a tiny measurable amount. He could read the strength of the force from the twist, separation by separation, mapping how the push grew as the gap shrank. The result matched Casimir's prediction. The force was there, it grew as the surfaces approached in just the way the theory said, and its strength agreed with the calculation to within a few percent, the level of precision the experiment could reach. Empty space was pushing on the plates by exactly the amount the trembling vacuum should produce. Later experiments by other groups, with still finer methods, tightened the agreement further, confirming the shape and size of the force across a range of distances. The Casimir effect was no longer a beautiful idea, it was a weighed and measured fact. Sit with what that means. A force was predicted to arise from the structure of empty space, from nothing more than the way two plates reshape the vacuum's zero-point ripples. 50 years later, a careful experimenter built an instrument delicate enough to feel that force directly, and found it exactly where theory placed it. The nothing between the plates was pushing, and the push could be put on a graph. There are not many moments in physics where an abstraction this deep is laid on a laboratory bench and confirmed by a twisting wire. The Casimir measurement closes a circle. We began this stretch of the story with the uncertainty principle forbidding the vacuum to be still, leading to zero-point energy, an idea that could have stayed forever in the realm of equations. Now we've held the consequence in our hands. Empty space trembles, the trembling carries energy, and that energy can press two metal plates together hard enough to measure. The vacuum is not a passive stage, it acts. And once you accept a vacuum that acts, that pushes and trembles and touches matter, a familiar everyday event takes on a hidden depth. When an atom gives off light, when a flame glows or a screen shines, the vacuum is quietly involved in that too, coaxing the light out of the atom in the first place. Think about a neon sign, or the gentle glow of a star, or any atom that has been given energy and then shines. We say the atom is excited, meaning one of its electrons has been kicked up to a higher rung on the energy ladder. After a short while, the electron drops back down to a lower rung and releases the energy it borrowed as a flash of light, a single particle of light called a photon. This is how most of the light around you is made, by electrons falling back down inside atoms and emitting photons as they go. It is called spontaneous emission, and the word spontaneous hides a real puzzle. Here is the puzzle. An excited atom, left entirely alone in perfect emptiness, with nothing around to disturb it, still eventually emits its photon and drops down. It does not wait forever. It does not need a passing wave of light to knock the energy loose. It simply, after some characteristic time, lets go on its own. But why should it? If the atom is truly isolated, sitting in calm, empty space, what tells it to release the light now rather than later, or at all? An electron resting on an upper rung, undisturbed, ought to be content to stay there. Something must be prompting it to fall. For a while this was genuinely mysterious, and the answer turned out to be the restless vacuum once again. The excited atom is never truly alone, because empty space around it is not truly empty. It is filled with the trembling electromagnetic field and its endless flicker of virtual photons. That ever-present field reaches into the atom and gives the electron a faint, ceaseless nudge, and it is this nudge from the vacuum that coaxes the electron off its perch and tips it down the ladder, releasing the photon. The atom does not glow entirely on its own. The vacuum draws the light out of it. There is a clean way to see that the vacuum is doing the work. Physicists discovered that you can change how fast an atom emits its light by changing the empty space around it. Place an excited atom inside a carefully built cavity, a tiny box whose size controls which vacuum ripples are allowed nearby, just as the Casimir plates controlled which ripples fit in their gap. Tune the cavity so that the vacuum ripple the atom wants to emit into is allowed, and the atom glows faster, releasing its light sooner. Tune the cavity so that ripple is shut out, forbidden by the size of the box, and the atom holds its energy longer, glowing more slowly, sometimes far more slowly. The atom's own internal clock has not changed. What has changed is the vacuum it sits in. Reshape the emptiness, and you reshape how the atom shines. This is a striking thing to be able to do, and it has a name, cavity quantum electrodynamics, and it is real laboratory work, not a thought experiment. By engineering the empty space around an atom, physicists speed up or slow down its glow at will. The light an atom gives off, which seems like the most intrinsic thing about it, the very colour and timing of its shining, is partly set by the structure of the nothing that surrounds it. So even the ordinary glow of matter carries the vacuum's fingerprint. Every flame, every star, every glowing screen owes the timing of its light, in part to the trembling of empty space coaxing electrons down their ladders. The nothing is not a silent witness to the light of the universe. It is a quiet midwife to it. We have seen the vacuum push on plates and draw light from atoms. Now we turn to how it bends the very forces between charged particles, acting like a faint shifting fog that wraps every charge in the universe. Take a single electron sitting alone in empty space, with its negative electric charge. The old picture is simple. The electron has a definite charge, a fixed number, the same whether you look at it from across the room or from very close up. But the seething vacuum changes this picture in a way that is subtle and real. Around that electron, the froth of virtual particles does not stay neutral and indifferent. It responds to the electron's charge, and in responding it wraps the electron in a faint shifting cloud that partly hides it. Here is how. The vacuum near the electron is constantly producing virtual pairs, an electron and a positron flickering into being together, then annihilating. Each such pair has a negative member and a positive member. In the brief instant they exist, the electron's own charge tugs on them. The negative virtual electrons are pushed gently away, and the positive virtual positrons are pulled gently inward, toward the real electron at the centre. So in the cloud surrounding any real charge, the opposite charges drift slightly closer, and the like charges drift slightly outward. The vacuum lines itself up very faintly, in response to the charge sitting in it. This lining up is called vacuum polarization, and it has a clear consequence. The layer of positive virtual charge that gathers close around our electron partly cancels, partly screens, the electron's negative charge, as seen from far away. From a distance, you do not see the bare electron. You see the electron wrapped in its polarized cloud, and the cloud hides some of the charge. The electron looks a little weaker than it truly is, its field muffled by the responsive fog of the vacuum around it. A fair, everyday handle is a charged object dipped in salt water. The water holds ions, positive and negative, free to move, and they rearrange around the charge, the opposite ones crowding close, screening it, so that from a distance the charge seems reduced. The vacuum does the same thing, but it needs no water and no salt. The screening medium is empty space itself, polarized by its own virtual pairs. The difference worth naming is that salt water is made of real ions you could filter out, while the vacuum screening cloud is made of virtual particles you can never collect, conjured from the uncertainty of the void and gone again in a flash. Now comes the part that turns us from a curiosity into something measurable. If the vacuum screens the electron's charge, then how much charge you see depends on how close you get. Stay far away, outside most of the polarized cloud, and you see the screened muffled charge, the value we normally call the electron's charge. Pushing close, burrowing inside the cloud of positive virtual charge, and there is less screening material left between you and the electron, so you see more of its true charge. The closer you get to an electron, the stronger its electric charge appears. This is not a guess. In powerful particle accelerators, physicists smash electrons together hard enough to probe them at extremely short distances, peering deep inside the polarized cloud. And there, up close, the electron's charge does measure stronger than it does at a distance, by exactly the amount the screening vacuum predicts. The strength of electricity is not one fixed number. It grows as you approach, because you're pushing through the vacuum's fog toward the bare charge at the center. The vacuum, then, is not just a place where forces happen. It shapes the forces themselves, screening every charge, making the strength of electricity depend on distance. And this idea that the strength of a force is not fixed but changes with how closely you look opens into one of the deepest features of modern physics, the running of the constants of nature. Physicists like to speak of the strength of a force with a single number, and for electromagnetism that number is the fine structure constant. It measures how strongly charged particles push and pull on each other and on light, and it is one of the most important numbers in physics. Its everyday value is close to 1 part in 137, a pure number with no units, the same in any system of measurement, which is part of why it has fascinated physicists for a century. Richard Feynman called it one of the great mysteries of physics, a magic number handed to us with no clear explanation of why it takes the value it does. But here is the twist the vacuum forces on us. That famous value, near 1 in 137, is not really a constant at all. It is the strength of electromagnetism measured at everyday distances, from far enough away that you see the electron's fully screened charge. Get closer, push through the vacuum's polarized fog, and the effective charge grows, which means the strength of electromagnetism grows too. The fine structure constant, the supposedly fixed magic number, slowly increases as you probe smaller and smaller distances, smaller and smaller separations between the particles you're studying. Physicists call this running, and they say the coupling runs with distance, or equivalently with energy, since probing short distances takes high energy collisions. It is a direct consequence of the screening vacuum from the last chapter. At low energy, at long range, you see the muffled charge and a weaker force. At high energy, at short range, you see more of the bare charge and a stronger force. In the most powerful collisions we can stage, the strength of electromagnetism climbs noticeably above its familiar 1 in 137 value, exactly as the polarized vacuum demands. The constant is not constant. It runs, and the vacuum is what makes it run. This running is not unique to electromagnetism. Every force whose carriers interact with the vacuum has a strength that runs with distance, and here the story takes a remarkable turn, because the strong force, which binds the cores of atoms together, runs the opposite way. For electromagnetism, screening makes the force grow stronger up close. For the strong force, a different and richer kind of vacuum response makes it grow weaker up close and stronger as you pull things apart. The carriers of the strong force, called gluons, fill the vacuum with a churn that does the reverse of screening, so the closer two quarks come, the more weakly they pull, and the farther apart you try to drag them, the harder the force resists. That backward running has a profound consequence, recognized with a Nobel Prize, and it explains one of the strangest facts in nature, that you can never pull a single quark out on its own. Try to separate two quarks, and the strong force between them does not fade with distance the way gravity or electricity does. It holds firm, even grows, so that pulling them apart takes ever more energy, until the energy you have poured in is enough to make a fresh pair of quarks from the vacuum, which snap onto the ends, and you're left with two pairs instead of one lonely quark. The vacuum reaches in and refuses to let a quark stand alone. So the running of the constants, born from the vacuum's response to charge, reaches from the gentle pull of electricity to the iron grip of the strong force. And that grip, that churning gluon vacuum inside every atomic core, holds a secret about you, about the weight of your own body that we turn to next. Most of your mass, it turns out, does not come from matter at all. It comes from the energy of the vacuum inside you. Here is a fact that sounds impossible the first time you hear it. Almost all of your weight, the heft of your body on a scale, comes not from the stuff you're made of, but from the energy of empty space churning inside you. To see why, we have to look inside the atom, past the electrons, into the dense core at its center, the nucleus, and then inside the particles that make up that core. The nucleus is built from protons and neutrons, and for a long time those were thought to be solid, simple lumps. They are not. Each proton and each neutron is itself made of smaller particles called quarks, 3 of them apiece, held together by the strong force we just met, the force carried by gluons. So a proton is 3 quarks bound in a churning cloud of gluons, and the strong force is energy. Now comes the astonishing part. Add up the masses of the 3 quarks inside a proton, the actual matter content, and they account for only a tiny fraction of the proton's total mass, around 1 part in 50. The other 98% or so is not matter at all. It is the energy of the strong force field, the churning gluon vacuum, bound up inside the proton. This works through the most famous equation in physics, Einstein's statement that energy and mass are 2 faces of the same thing, that energy has weight and mass is a form of stored energy. Inside the proton, the strong force field carries an enormous amount of energy, the gluons and the quarks racing and churning in a furious confined storm. That energy, by Einstein's rule, has mass, and that field energy, that bottled up churn of the strong vacuum, is where almost all the proton's mass comes from, and therefore almost all of yours. The quarks supply a sliver. The roiling field supplies the rest. Let the scale of this land. Step on a bathroom scale and read your weight. Only a % or 2 of that number traces back to the actual mass of the fundamental matter particles inside you, the quarks. The other 98% is the energy of the strong force fields churning inside every proton and neutron of every atom of your body, weighed by Einstein's equation. You are almost entirely bottled energy. The The solid heft of view is mostly the confined storm of the strong vacuum, made heavy by the link between energy and mass. A rough handle helps here, though like all such handles it has a limit. Picture a sealed box of fast-moving gas. The gas molecules race around inside carrying energy of motion, and that trapped energy adds, very slightly, to the weight of the box. The proton is something like that box, except the trapped energy is not a faint addition, but nearly the whole of the mass, and the racing contents are not gas molecules but quarks and gluons held in the unbreakable grip of the strong force. The box is mostly the energy it confines. This overturns a comfortable intuition. We tend to think mass is just how much stuff a thing contains, how much matter you would count if you could tally every particle. For the everyday world, almost all the mass is something subtler. The energy of fields locked inside the particles of matter, a churning vacuum of the strong force that weighs nearly the whole of an atom. Your solidity is borrowed from the restlessness of empty space inside you. But this is only one of the two great ways the vacuum gives things mass, and it is not the one you may have heard about. The quarks themselves, and the electrons, have their own small masses, and those come from a different source entirely, from a second field that fills all of space and slows particles as they move through it. That field has a name now famous far beyond physics, the Higgs. The story of the Higgs field begins with a problem in the equations of particle physics in the 1960s. The mathematics that so beautifully describe the forces of nature worked cleanly only if the fundamental particles had no mass at all, if every electron and every quark raced along at the speed of light, weightless. But of course they do not. Electrons have mass. Quarks have mass. The particles that carry the weak force, which governs certain kinds of radioactive decay, have large masses. The equations wanted a massless world, and the real world was full of mass. Something had to give the particles their weight without wrecking the beautiful symmetry of the equations. The answer, proposed by several physicists working separately around 1964, among them Peter Higgs, François Englert, and Robert Brute, was to add one more field to the universe. This new field, unlike the electromagnetic field, does not rest at zero in empty space. It settles instead at a value that is not zero, everywhere, filling all of space with a constant, steady presence even in the deepest vacuum. Empty space is soaked in this field, the way a sponge is soaked in water, and every particle that moves through space moves through it. And here is how it gives mass. Particles interact with this field as they travel, and the interaction acts like a kind of drag, a resistance to being pushed around. A particle that interacts strongly with the field finds it hard to change its motion. It resists acceleration, and resistance to acceleration is exactly what we mean by mass. A particle that interacts weakly with the field slips through more easily and has little mass. A particle that ignores the field entirely, like the photon, stays massless and races along at light speed. The field is everywhere, and a particle's mass is a measure of how much that everywhere field grips it as it goes. The comparison often reached for is a crowd in a room. Imagine a famous person trying to cross a crowded party. People cluster around them, slowing their progress, so they move as though they were heavier, harder to get going and harder to stop. Someone unknown crosses the same room freely, ungripped, light on their feet. The field is the crowd filling the room, and a particle's mass is how much the crowd clusters around it as it tries to move. The handle has a limit, as all of them do. The Higgs field is not made of separate people, and it does not slow a particle to a stop the way friction would. It sets how much the particle resists changes in motion, its mass, not a gradual dragging to rest. For decades, this was a beautiful idea with no direct proof. The way to confirm it was to find the field's own particle. Every fundamental field has a particle associated with it, a ripple in the field, and the Higgs field should have one too, the Higgs particle, often called the Higgs boson. Finding it would mean the field was real. The search took half a century and required building the largest machine humanity has ever made, the Large Hadron Collider, a ring 17 miles around buried beneath the border of France and Switzerland, smashing protons together at nearly the speed of a light to shake a ripple loose from the Higgs field. In 2012, they found it. The Large Hadron Collider produced the Higgs boson, right where the theory said it should be, and the field that fills all of space and hands particles their mass was confirmed as real. Empty space, it turned out, holds yet another presence, a field that never switches off, quietly setting the mass of every electron and quark in your body. And the fact that this field rests at a value that is not zero points to one of the deepest ideas about the vacuum, the idea that empty space had to choose. Why does the Higgs field rest at a value that is not zero, while the electromagnetic field rests at zero? Why would a field left alone in empty space settle anywhere other than nothing? The answer is one of the most beautiful ideas in modern physics, and it goes by the name spontaneous symmetry breaking. It explains how empty space can quietly pick a state, and in picking it, shape the laws that govern everything inside it. Start with a picture. Imagine a marble sitting at the very top of a smooth, rounded hill, a hill shaped like the bottom of a wine bottle, with a raised bump in the centre and a circular trough running all the way around. Right at the top of the central bump, the marble is perfectly balanced and perfectly symmetric. Every direction looks the same to it. There is no left or right, no favoured way to fall. But that balanced point is unstable. The slightest nudge sends the marble rolling down off the bump and into the trough, where it comes to rest at some particular spot along the circle. The moment it settles, the perfect symmetry is broken. The marble is now at one specific place, and a direction has been singled out, even though every direction was equally likely before it fell. The crucial thing is that the symmetry was not destroyed by any outside force. The hill is still perfectly symmetric. The laws did not change. The marble simply could not stay balanced at the symmetric point, and in rolling down it had to choose, and the choosing broke the symmetry on its own, spontaneously. The underlying rules stay symmetric while the actual state of things does not. The Higgs field does exactly this. The laws governing it are symmetric, and the value 0 sits at the top of the central bump, balanced but unstable. The field cannot stay there. It rolls down into the trough and settles at a value that is not 0, filling space with that non-zero value, the soaked sponge vacuum we met in the last chapter. Empty space picked a state, the way the marble picked a spot, and that choice is why particles have mass. The vacuum chose, and the consequences ripple through all of physics. This idea reaches far beyond the Higgs. Again and again in nature, a system whose laws are perfectly symmetric ends up in a state that is not, because the symmetric state is unstable, and the system must settle somewhere. A magnet shows the same thing. Above a certain temperature, its atoms point every which way, perfectly symmetric, no direction preferred. Cool it down, and the atoms must align, and they pick a direction to point together, breaking the symmetry, even though no direction was special beforehand. The magnet, like the vacuum, falls into one choice out of many equally good ones. So the vacuum is not a neutral, indifferent backdrop that simply allows physics to happen on top of it. The vacuum is in a chosen state, one of many it could have fallen into, and that choice helps set the very laws we observe, which particles have mass, how the forces divide and behave. Change the vacuum's chosen state, and you would change the rules of the world. The emptiness is not lawless. It made a decision long ago, and we live inside the consequences of that decision. This raises a question that has haunted physics for a century, and it pulls us from the smallest scales out to the largest. If empty space holds all this energy, the zero-point trembling, the churning fields, the chosen Higgs value, then that energy should have weight, and weight bends space and pulls on the whole universe. So what does all the energy of the vacuum do to the cosmos itself? The first person to put energy into empty space on a cosmic scale was Einstein, and he called it the greatest blunder of his life. In 1917, Albert Einstein was applying his new theory of gravity, general relativity, to the whole universe at once, the most ambitious thing anyone had ever tried to calculate. general relativity says that matter and energy bend space and time, and that this bending is what we feel as gravity. When Einstein worked out what his equations said about the universe as a whole, he found something that troubled him deeply. The equations would not allow a static universe. Gravity, always attractive, pulling every bit of matter toward every other bit, should make the whole universe collapse inward on itself, or else fly apart. It could not simply sit still. But in 1917, everyone, Einstein included, believed the universe was static, eternal, and unchanging on the larger scale, neither growing nor shrinking, nor the stars had always been there and always would be. So Einstein did something to force his equations to allow a stable, unchanging universe. He added a new term, a constant, which he called the cosmological constant. It acted as a kind of outward push built into space itself, a repulsion spread through all of empty space that could exactly balance the inward pull of gravity and hold the universe still. In effect, he gave empty space an energy of its own, a tendency to push outward, tuned precisely to keep everything in balance. It was a fix, an addition made to match what people believed about the universe. And then, a little over a decade later, the belief collapsed. The American astronomer Edwin Hubble, studying distant galaxies through the Great Telescope at Mount Wilson, found that they were nearly all moving away from us, and the farther away a galaxy was, the faster it was receding. The universe was not static at all. It was expanding, every galaxy rushing apart from every other, the whole cosmos growing larger with time. There had been no need to balance gravity against a static universe, because the universe was never static. Einstein, the story goes, called the cosmological constant the greatest blunder of his life. He had patched his equations to hold up a static universe that did not exist, and in doing so he had missed a chance to predict the expansion before Hubble found it. Had he trusted his original equations, which refused to allow a static cosmos, he might have foreseen that the universe must be growing or shrinking, one of the great predictions he could have made and did not. He took the term back out, set the cosmological constant to zero, and treated empty space as carrying no energy of its own after all. For most of the 20th century, that is where the matter rested. The cosmological constant was Einstein's embarrassing mistake, quietly set to zero and largely forgotten, a wrong turn on the way to understanding the expanding universe. Empty space, on the cosmic scale, was once again treated as truly empty, weightless, contributing nothing to the great pull and push of the heavens. But the idea would not stay buried, and here is the deep irony at the heart of this chapter. Einstein had added energy to empty space for the wrong reason, to prop up a static universe, and he had been wrong about that. Yet the basic notion that empty space might carry an energy of its own that pushes the cosmos outward was about to return in a form Einstein never imagined, driven not by a desire for balance but by a discovery no one was looking for. At the very end of the century, astronomers measuring exploding stars in distant galaxies would find that empty space really does push, and that the universe is not just expanding but speeding up. In the late 1990s, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone expected it to be slowing. The universe had been expanding since the Big Bang, and gravity, pulling all the matter together, should be acting like a brake on that expansion, gradually reining it in. The only question seemed to be whether gravity would eventually win and pull everything back into a collapse, or whether the universe would coast outward forever, ever more slowly. Both teams were trying to measure the rate of the slowdown, a careful, almost routine piece of cosmic bookkeeping. To do it, they needed a way to measure vast distances across the universe, and they found it in a particular kind of exploding star, a type of supernova that always detonates with very nearly the same true brightness. Because every one of these explosions shines with nearly the same intrinsic power, you can tell how far away one is by how bright or dim it appears from Earth. The dimmer it looks, the farther away it must be. And because light takes time to travel, the farther away a supernova is, the further back in time you're seeing. So distant supernovas show you how fast the universe was expanding long ago, while nearby ones show the rate more recently. Compare the two, and you can read off whether the expansion has been speeding up or slowing down. Both teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, gathered their distant supernovae and worked through the measurements, expecting to find the expansion gently slowing. In 1998, they found the opposite. The distant supernovae were fainter than they should have been, which meant they were farther away than a steadily slowing expansion would place them. The universe had not been coasting to a gentle stop. At some point in the past several billion years, the expansion had stopped slowing and begun to accelerate. The galaxies are flying apart faster and faster as time goes on. This was a genuine shock, checked and rechecked because it was so unexpected, and it held. Something is pushing the universe apart, overpowering the inward pull of all its gravity, and growing in influence as the cosmos thins out. Whatever it is, it acts like an energy spread evenly through all of space, pushing outward everywhere, exactly the kind of thing Einstein's cosmological constant described. The term he had added and regretted, the energy of empty space, was back. Not to hold the universe still, but to drive it apart. We now call this pushing influence dark energy, and by every measurement it makes up most of the universe, far more than all the matter, dark or ordinary, combined. The discovery won the Nobel Prize, and it rearranged our picture of the cosmos. The universe is not mostly stars and galaxies. It is mostly this dark energy, this push built into empty space, with everything we can see floating as a thin froth on top of it. And the simplest explanation for dark energy is exactly the vacuum energy we have been building toward all along. The trembling zero-point energy of all the fields, summed across all of space, weighing on the cosmos and pushing it apart. Einstein's blunder, it seemed, was half right after all. Empty space does carry energy, and that energy shapes the fate of the universe. But when physicists tried to calculate how much energy the vacuum should hold and compare it to how much dark energy they actually measured, they ran headlong into the single worst prediction in the history of science. We have two ways to ask how much energy empty space contains, and they ought to agree. One way is to measure it, by watching how fast the universe accelerates, since the dark energy driving that acceleration is the energy of the vacuum at work on the larger scale. That measurement gives a real number, small but definite, a faint push spread through all of space. The other way is to calculate it, by taking the zero-point energy of all the quantum fields, the trembling we have followed through this whole story, and adding it up across all the ripples the vacuum can hold. These two numbers, the measured and the calculated, should match. They do not. They miss each other by a margin so vast it is hard to write down or even to picture. When you add up the zero-point energy of the fields the straightforward way, summing the contributions of every possible ripple down to the smallest scales physics describes, the total comes out staggeringly large, an energy density for empty space so enormous it defies imagination. When you measure the actual energy of the vacuum from the gentle acceleration of the universe, you get a number that is fantastically, absurdly smaller. The gap between the calculated value and the measured value is often quoted as a factor of 10 to the 120th power, a 1 followed by 120 zeros. There is no honest comparison in ordinary life for a mismatch that large. It is not like missing a guess by a little, or even by a lot. It is like calculating the weight of a single grain of sand and getting an answer heavier than the entire observable universe many times over. This is the vacuum catastrophe, and it is routinely called the worst prediction in the history of physics, because no other calculation in science is so far from the measured truth, while coming from theories that otherwise work superbly. The quantum field theory that gives the absurd answer is the same theory that predicts the electron's magnetism to 12 decimal places. The cosmology that gives the tiny measured answer is built on general relativity, which has passed every test thrown at it. Both pillars are rock solid on their own. bring them together to ask how much the vacuum weighs, and they disagree by a factor beyond all reason. It is worth being honest about what this means, because it is easy to gloss over. It does not mean the vacuum energy is fake, or that the trembling we have followed is wrong. The zero-point energy is real, confirmed by the Casimir force, the Lamb shift, and more. The trouble is the total, the grand sum of all that energy across all of space. Something we do not understand keeps that total almost entirely from gravitating, from weighing on the universe the way the calculation says it should. Nearly all of the enormous calculated energy must somehow cancel out or fail to count, leaving only the faint whisper that actually drives the cosmic acceleration. We do not know what does the cancelling, or why it leaves behind exactly the small amount it does. This is not a sign that physics has failed. It is a sign that something deep is still missing, a piece of the picture not yet found, sitting right at the join between the quantum world of the very small and the gravity of the very large, the two great theories that have never been fully reconciled. The vacuum catastrophe may be a clue pointing toward that missing reconciliation, a place where the unfinished nature of physics shows through most starkly, and the puzzle has a second, sharper face. It is strange that the calculated energy is so huge. It is stranger still that the measured energy, though tiny, is not exactly zero, and that its small size seems almost impossibly fine-tuned. Set aside the enormous calculated number for a moment, and look only at what we measure. The energy of empty space, read from the acceleration of the universe, is not zero. It is a small positive number, faint but real, and the strangeness is not just that it is small. The strangeness is how delicately small it is, how finely balanced, in a way that seems to call for an explanation we do not have. This is the cosmological constant problem, and it is one of the sharpest puzzles in all of physics. To feel the trouble, think about what goes into that final measured number. The vacuum energy is a grand total, a sum of many large contributions. The zero-point energy of the electromagnetic field, the zero-point energy of the electron field, the quark fields, every field there is, the energy locked in the Higgs field's chosen value, the churning energy of the strong force vacuum. Each of these contributes its own piece to the total energy of empty space, and each piece calculated on its own is enormous, the kind of huge number behind the vacuum catastrophe. Some of these pieces are positive, pushing the total up, and some are negative, pulling it down. Now here is the knife edge. The final measured energy of the vacuum is fantastically smaller than any of the individual pieces that go into it. That means all those enormous positive and negative contributions must very nearly cancel each other out, adding up to almost exactly zero, but not quite zero. They must cancel to something like 120 decimal places, an agreement of staggering precision, leaving behind only the faint whisper we measure. If the cancellation were perfect, the vacuum energy would be zero, and the universe would not accelerate. If the cancellation were off by even a tiny amount in those far decimal places, the vacuum energy would be enormous, and the universe would have torn itself apart or collapsed, long before any galaxy or star or living thing could form. This is what physicists mean when they say the value looks fine-tuned. It is as if dozens of huge numbers, with no apparent reason to coordinate, conspired to cancel almost perfectly, landing on a result just barely above zero, and just right for a universe that lasts long enough to hold us. Nothing in our current theories explains why the cancellation should come out this way. The numbers do not have to add up so kindly. They simply do, and we do not know why. A common everyday handle, imperfect as ever, is a long ledger of enormous deposits and withdrawals, sums in the trillions, that at the end of the day balance to within a single penny, again and again, with no accountant arranging it. You would suspect something was guiding the books. In the case of the vacuum, we have found no accountant, no principle that forces the cancellation. The fine smallness of the vacuum energy sits there as a brute fact, measured but unexplained. Physicists have offered ideas. Perhaps some undiscovered symmetry forces the cancellation. Perhaps the value is set by chance among a vast landscape of possible universes, and we find ourselves in one of the rare ones where the number came out small enough to allow life, simply because the others have no one in them to look. These ideas are debated, and none is settled. The cosmological constant problem remains genuinely open, a place where we can measure something to great precision and still have no idea why it takes the value it does. We have followed the energy of empty space from a faint trembling to the force that shapes the fate of the universe. Now we turn that energy loose at the very beginning of time, to a moment when the vacuum itself may have held a huge energy, and, in the briefest instant, blown the infant universe up to enormous size. To explain the universe we actually see, cosmologists were driven to a striking idea about the vacuum of the very early universe, an idea called cosmic inflation, proposed by the physicist Alan Guth around 1980 and developed by others soon after. The puzzles it answered were real. The universe looks remarkably uniform on the larger scales, nearly the same temperature in every direction, even between regions so far apart they should never have been in contact. It is also remarkably flat, its geometry balanced on a knife edge between curving in on itself and spreading open. These features were hard to explain by ordinary expansion alone. Something must have happened very early to smooth the universe out and flatten it. Inflation's answer rests on the vacuum. Suppose that in the first unimaginably tiny fraction of a second, the universe was filled not with the low-energy vacuum we have today, but with a vacuum holding a very high energy, a field sitting temporarily in a state far up the hill rather than down in the trough. A vacuum with that much energy behaves in an extraordinary way under Einstein's gravity. Its energy pushes outward, like dark energy but vastly stronger, and it drives the universe to expand not steadily, but explosively, doubling in size, then doubling again and again, faster and faster, in a runaway swelling that repeats many times over in a sliver of a second. The numbers, even softened into words, are staggering. In far less than the blink of an eye, in a stretch of time so short it makes a billionth of a second look like an age, inflation may have stretched a patch of the early universe smaller than a single atom up to a size larger than a grapefruit, and in doing so expanded the whole cosmos by a factor beyond ordinary counting. A region tiny enough to be smoothed perfectly even, where every part had been in contact, was blown up so enormously that it became everything we can see and far more, which is why the sky looks so uniform in every direction. The flatness follows too, because stretching anything by such a colossal factor flattens it. The way the ground beneath your feet looks flat because the Earth is so large. Then, almost as soon as it began, inflation ended. The high-energy vacuum decayed, rolling down off its perch into the low-energy state we live in now, and the huge energy it had been holding was released, poured out as a blast of particles and radiation that filled the universe with hot matter. That release was, in effect, the beginning of the hot, dense universe we usually picture as the Big Bang. The vacuum, having blown the cosmos up to enormous size, dumped its energy and lit the fire of everything that followed. And inflation left one more gift, the deepest of all. During that brief swelling, the ordinary quantum trembling of the vacuum, the zero-point ripples we have followed throughout this story, were stretched along with everything else, blown up from the tinier scales to enormous ones, and frozen in as faint variations in the density of the early universe. Those stretched ripples became the seeds of structure. Where the vacuum had trembled slightly more, matter later gathered slightly more thickly, and over billions of years those faint seeds grew into galaxies, clusters, and the great cosmic web. The galaxies in the sky, including our own, may be the zero-point trembling of empty space, magnified by inflation and made solid by time. If this picture is right, then the vacuum is not only the background of the universe, but its origin and its architect, the thing that swelled the cosmos up, lit its fire and sketched the pattern of everything in it. Which forces a sobering question. If the vacuum once sat in a high-energy state and fell to a lower one, Could the vacuum we live in now do the same? The unsettling idea is called vacuum decay, and it follows from taking spontaneous symmetry breaking seriously. Recall the marble that had to roll off the unstable bump and settle in the trough. We assumed it settled at the lowest point, the true bottom, the most stable state there is. But what if the trough where our vacuum settled is not the true lowest point? What if there is a deeper valley somewhere, an even lower energy state, and our vacuum is merely resting in a dip partway down, stable for now but not truly at the bottom? A vacuum like that is called a false vacuum, and the deeper state below it is the true vacuum. A false vacuum can sit quietly for an immense span of time, looking perfectly stable, the way a marble can rest in a small dip on a hillside without rolling further, held in place by a low ridge in front of it. But the quantum world has a trick that the everyday world does not, called tunneling, in which a system can pass through a barrier it does not have the energy to climb over, simply appearing on the other side. Given enough time, a false vacuum can tunnel through the ridge, and somewhere, in some tiny region of space, a bubble of the true, lower vacuum can suddenly form. Whether our vacuum is false, and whether it is stable or merely long-lived, is an open question, and intriguingly the measured mass of the Higgs particle places our universe tantalizingly near the boundary between stable and not. If such a bubble ever formed, here is what the physics says would happen. The bubble of true vacuum, being lower in energy, would be favoured over the false vacuum around it, so it would not collapse back. It would grow, its walls sweeping outward, and because the drop in energy is enormous, that wall would race outward at nearly the speed of light. Inside the bubble, the laws of physics would be subtly different, set by the new, lower vacuum, and almost certainly hostile to matter as we know it, so that atoms could not hold together. The bubble would expand, converting the universe to its new state as it went, and anything it reached would be remade or destroyed. Sit for a moment with how strange and quiet a catastrophe this would be. Because the bubble wall travels at nearly the speed of light, it would arrive at almost the same instant as any warning of it, any light or signal announcing its approach. There would be no sight of it coming, no gathering shadow, no time to react. The first and only sign would be everything, all at once, ceasing to be as it was. It is the most complete ending physics can describe, and it would unfold without a sound and without a herald. This sounds like the bleakest possible note, and it is worth holding it honestly but also in proportion. As far as we can tell, no such bubble has formed anywhere in the visible universe in nearly 14 billion years, despite all that time and all that space. If our vacuum is false, it is extraordinarily long-lived, stable on timescales that dwarf the current age of the universe many times over. The calculations carry large uncertainties and rest on assuming we know all the relevant physics, which we may not. This is a real possibility taken seriously by physicists, not a forecast of anything near. It is a statement about the deep stability of empty space, and about how much rests on the vacuum sitting truly, and not just apparently at the bottom. Whether or not the ground ever gives way, the vacuum has a long future ahead of it, and that future, the slow cold fate of empty space, is where our climb finally levels out. Let us follow the universe forward, far past any human reckoning, and ask what becomes of empty space in the end. The expansion we measured through the supernovae is not slowing. Driven by the vacuum's dark energy, it is speeding up, and if dark energy holds steady, that acceleration will continue without end. Over immense spans of time, the consequences are profound and quiet. Distant galaxies, carried apart by the swelling of space, will recede faster and faster until their light can no longer reach us at all. One by one, the galaxies beyond our own neighbourhood will slip past the edge of what we can ever see, dimming and reddening and finally vanishing, until the sky beyond our local group of galaxies goes dark and empty. The stars themselves will not last forever. Stars form from gas, and the supply of fresh gas is finite. In time, star formation will slow and then cease. The last stars will burn through their fuel and die, the smallest and longest lived among them, flickering out after trillions of years. The universe will grow dark, lit only by the fading embers of dead stars, the cooling cinders of what once blazed. Matter itself may not be eternal, as over almost inconceivable spans even atomic nuclei may break down, and the black holes that remain will themselves slowly evaporate, glowing faintly away over spans of time that make the present age of the universe seem like nothing at all. What remains at the far end of this long cooling is mostly empty space, stretched vast and thin and cold near the lowest temperature physics allows but never quite reaching it. This is the state often called the heat death of the universe. A cosmos spread so wide and cooled so far that nothing happens anymore. No stars, no structure, no flow of energy from warm to cold to drive any change. Everything that could happen has happened, and what is left is darkness and distance and an almost perfect stillness. An emptiness far emptier than the one we began this story trying to understand. And yet, after everything we have followed, you already know the final twist. Even that vast cold emptiness will not be truly still. The vacuum will still hold its 0-point energy. The trembling, the uncertainty principle forbids it ever to lose. The fields will still flicker faintly with virtual particles, borrowing and repaying energy as they always have. Empty space at the end of time will hum at the same irreducible level it hums at now, because that hum is not something the universe can run out of or cool away. It is the floor of reality, the least the fields are allowed to do, present at the beginning and present at the end, unchanged while everything else fades. There is a strange comfort in that, and a strange grandeur. The stars are temporary, the galaxies are temporary, matter itself may be temporary. The one thing that endures, from the first instant through the long cold after, is the restlessness of empty space, the faint, ceaseless trembling we have spent this whole journey learning to see. The vacuum outlasts everything it gives rise to. The nothing is the most permanent thing there is. So we have followed empty space from the everyday feeling that it is simple absence, all the way to a trembling, energetic, world-shaping presence that was here before the stars and will remain after them. Only one task is left, to return to the plain question we started with, and answer it as simply as we now can. What, after all of this, is really there inside the nothing? We began with your hand held up against the air, and the simple feeling that the space just past your fingertips is empty, plain absence, a container waiting to be filled. That feeling served humanity for thousands of years, and there is no shame in it, because at the everyday scale it is nearly true. But we have followed the question down, layer by layer, and we can now answer it plainly. The nothing is not nothing. Empty space is filled with fields that can never be switched off. Trembling with a 0-point energy the uncertainty principle forbids them to lose, flickering with virtual particles that borrow energy and vanish, holding the chosen value of the Higgs that gives particles their mass, and carrying the dark energy that pushes the whole universe apart. When you take everything out, what remains is not absence. It is a restless, structured, energetic thing, perhaps the most energetic and most permanent thing there is. Hold the whole climb in your mind for a moment. The atomists argued the void must exist while Aristotle swore it could not. Torricelli made the first patch of real emptiness at the top of his Mercury column, and Guericke's horses could not pull his empty sphere apart. The 19th century filled space with an ether to carry light, and Michelson and Morley went looking for that ether and found nothing, until Einstein cleared it away and left a space that still had structure. Then Planck found energy comes in lumps. Heisenberg forbade the field from ever holding still, and the trembling vacuum was born. Dirac found antimatter hiding in it. The Lamb shift proved it touched atoms, and Casimir's plates, weighed by Lamoureux, let us feel its push. The same restless vacuum screen's charge gives most of your weight, breaks symmetries, drives the cosmos apart, and may have blown the universe up at the start of time. Every step rested on the one before it, and each was the work of real people looking a little closer than those before them. So what does this mean for you, standing here, made of atoms, holding up your hand? It means that the emptiness inside you and around you is not a backdrop to your life, but a participant in it. The vacuum gives nearly all your weight, through the churning energy bound inside every proton of your body. It sets the mass of your electrons through the Higgs field you're soaked in. It draws the light from every atom that glows, and it shaped the galaxies whose stars made the carbon and oxygen you are built from, growing them from its own faint trembling stretched across the early universe. You're not a thing sitting in empty space. You are, in a real sense, something empty space does, a pattern raised up out of its restlessness for a little while. And the question we open with has a final, honest edge. We can measure the vacuum's push, weigh its force, calculate its trembling to 12 decimal places, and still we cannot say why its total energy comes out as small as it does, or whether the ground beneath it is the true bottom or merely a resting place. The nothing keeps its deepest secrets even now. That is not a failure. It is an invitation, the same one that pulled Torricelli to tip his tube and Michelson to chase his wind. The sense that there is always one more layer to the thing we casually call empty. So the next time you look at the space just past your fingertips and it seems to hold nothing at all, you will know better. It is humming. It is trembling. It was here before the first star and will be here after the last one fades. The nothing is full, and you are part of what it became.